Okay, hello everyone. My name is Ferid Moradi, a PhD student at Samalarda University. Today I'm going to present you our detection system that uses tiny digital twin to detect a cyber attack. I'm working with Marjan and Sarah at the school, and the content of this presentation is based on our two papers. The first paper is security analysis at design time, and the second one is security analysis at runtime. Based on our goal, that is attack detection and prevention, we have runtime monitoring that we're doing that at the runtime when the system is operation, and with the tiny digital twin, that is the formal model that we are generating by model checking. We use this method because this method provides concrete and valuable reports for them in safety and security engineering, and also can make attack detection process simple and systematic. And when we're using these formal methods, that the result of the detection system reduces the false positive rate that currently exists in the intrusion detection systems. Basically, we are working on the cyber physical system. Cyber physical system is the integration of the physical layer that includes the sensors and actuators that handle the processes by giving the control commands that coming from the software components. Here is the controllers. There are feedback control loop between this physical layer and the software layer. An example of these systems are the transportation, robotics, or production system that provide a service or product. Because these component layer or software layer have vulnerabilities and exploited by the attackers, we can see some incidents or bad impact in the physical layer. So our solution, our main idea is developing the one software module that is placed between the controllers and these physical devices, listening to the sensor data and control commands, and decide if these packets or the sensor data control command are behaving based on that developed model or not. If we find one mismatch with these sensor data and control commands, with those transition are modeled in this tiny digital twin, we alert the system and also stop the execution and provide some reports that shows the source of the attacks. Okay, in order to build this monitor plus the tiny digital twin, we follow 3 steps. At the first step, we are using the model checking. Here, we developed our system, specify our system in the Rebeca code, and doing the model checking with Afra and generate one state space. This state space includes all state of the system, actually the possible behavior of the system. And then because this state space is usually huge and includes the internal and the external behavior of the system, all of the interaction between the components, we reduce the state space based on the observable traffics or the sensor data control commands that monitor can see between these 2 layer, I mean the physical layer and the software layer. And then we call these abstract model or abstract version the tiny digital twin. Then in order to use this abstract model as module at the runtime, we're using the lingua franca language that Edward will explain about this language, and generate one executable code that based off this digital twin react to the system to detect and prevent against the attacks. Okay, let's look at the first step. We're developing our system in the Rebeca modeling language that is the language specifically for the distributed system and concurrent system. This language has one embedded model checker that call it Afra. There is an IDE. It can be used easily for developing the model and its property, and could be checked in this IDE and see the result if the properties are violated or not. And also in the homepage of the Rebeca and Afra, shows the projects are developed and have some frameworks based on this language and successful work. They are showing that these in this homepage. And I should emphasize that these Rebeca language and also LF language both are the actor model. So I have one simple slide here that show how the actor are behaving. Actor are entities that communication between the actors is by message passing. And computation are modeled by taking those messages from the queue and handling these messages. Each actor in the Rebeca has message servers, state variables, and queue. Assuming these actor 1 send 2 messages to actor 2, these messages are stored in the queue, and then the message server responsible for those messages take those messages and handle it. These specification or these scenario are the method for developing this kind of the system that that entities has an interaction with each other. And step 2 is about the abstraction. We developed a tool that get the state space generated by model checking and the list of the label of the transition that related to the observable packets that sensing data and control commands, and abstract the whole state space based on these observable transitions. And we generated this small model that we call it tiny digital twin. These tiny digital twin have a branching biosimulation relation with the original state space. It preserves all branches or traces or passes that the system follows to in the execution time. Yes, this is an example of the one output of these two. The transition system at the right side is the one example of the state space, and we abstract these state space based on the time transition and those control commands. When we reach these abstract state transition on the left side with the tau transition and those observable. Here we hide the internal action and just we make it observable those timing transition and observable transition for the monitor. Step 3 is LF. LF is a programming language based on the reactors. It is developed for programming the cyber physical system. It has timing features that enable us to connect the logical time are used in the model to the physical time that exists in the application. Physical time, it means the clock of the system. So that this language help us to use those estimation of the time we are specifying on the model, connected and synchronized with the clock of the system at the runtime. This language is a meta language. It's the developer can use the currently C, C++, Python, or TypeScript as the main language to develop their own code. And the compiler of the LF translate the code, compile the code to the executable version by developing the code in these languages. This is the idea for the LF that currently we developed one of our project in the C++ languages, have the interactive visualization, and we can emphasize or connect which time we are connecting in this code. And yeah, one thing is important, and we use it in this method, that the Rebeca code is a Java-like languages, and we have the one mapping between the Rebeca and the LF. Both are actor-based languages, and this mapping is so simple, and the features and constructor of this language can be converted to the LF language. We examined and evaluated our method in the different case studies. We have 3 case studies here. The first one is the water treatment system that the system is providing or servicing the clean water. The second one is the pneumatic system. It's a connection between some cylinder that pick and place a different object in a different location. And the third one is the temperature control system for regulating the temperature in one room. I choose the first case to explain the detail of our method and show the code. Yes, this case study is placed in the iTrust in Singapore and have a different valves, pumps, and water tanks. In the PLC cabinet, we have the different PLCs and controlling water level of each tank. And each water tank have one sensor that report the level of the water to the PLC. The security issue is that the mechanism, password-based authentication mechanism is used to controlling that these wireless channels can be exploited by the attackers and performing the eavesdropping or dropping the packets or false data injection in this channel. And the result of this attack could be the damages over the water level in each tank that is overflow or underflow. So safety requirements for this system is taking the control of the level of the water in each tank. At the first level, from the model checking, we want to take care of these stuff by the model checking. So we want to build a model based on the specification. We abstract the architecture of the system and develop the one actor model. Each actor is a representation of each component in this system, PLCs, pumps, valves, and those messages represent the message passing between these components. Then in order to do the security analysis at the design time, we show which point or which component are vulnerable to security to perform a testing or security analysis. We perform the security analysis by categorizing three types of the attacks: attack on the component, attack on the channels, and combination of these attacks. Attacks on the channels is developed by developing one actor as a component that inject a different malicious message between the components in the different time. And the attack on the components is modeled by developing the one compromised version of the safe component that behaving has a malfunction. And the combination of both of these attacks can represent the complex attacks, and we involving in the model to check the system and see the result. We follow these three attacks based on the stride threat modeling. We categorize these attacks in the security objectives are presented in the stride threat modeling. For this case study, we implement the injection attack, that is a false data or the commands that targeted in the different channels and the component, and find 1,000 vulnerabilities in this system. For doing that, we developed the Rebeca code. As you see that we develop each component in this code. It's a Java syntax. And we write the properties as assertion here that are the overflow and underflow. We involve the attack model to this system model to do a model checking and reach the one safe or reliable model that we can use it at the runtime. So the state space generated here is attack free. Then we use this state space to be abstracted based on those observable traffics or sensing or commands. So we using these abstraction tool and getting the label of those commands and the sensors and abstract this model based on these observable traffic. And the generated one state space, we call it tiny digital twin. As you see, the generated tiny digital twin is around 86 state and 170 transition rather than these big state space. And in the last step, we developed the monitor module. This is the developed module for this system that gets input of the actually the traffic going to the controllers and the outputs that coming from the controllers to be sent to the physical layers. And this tiny twin is loaded at the first time when the system starts the execution. It's the one time we load the tiny twin and use it at the runtime. And when there is this monitor, if see the one mismatch within model and these traffic send out the one alarm. Yes, this is a mapping between the system that developed for the modeling and the LF code, and we use it as a simulation and testing these monitor. Here I show you this system as simulated that these three PLC are listening to those sensor, getting the data and deciding which command should be transferred to the actuators. I simulate the one attack that is injection attack in the system. The green screen is a monitor. As we injected the attack, the monitor checked that this is not the right traffic, so alarm the system and stop the execution. Yes, currently we are only detecting and preventing attack, and what we want to do is doing the adaptation technique for updating this tiny digital twin at the runtime, and also provide a mitigation plan that recover the system after attack, and using the machine learning techniques to improve the detection rate of these monitor module, and finally provide some backtracking techniques that help to the developers to track the source of the attack based on the reports are generated by the monitor. Okay, thank you.